microphone couldn't certainly not be here, but you talk to us about alpha beta sets and embeddings of self-similar sets. Fine,
okay. So thanks for the invitation. I'm sorry that I couldn't come. There was a scheduling conflict, and I would rather be there, but I hope this will go over okay on Zoom. So I guess I can hear you, so you can just ask questions from the audience if you have one. Good. And I can also write bigger. I've decided to do, I prefer Blackboard talks, so this is going to be a tablet talk. And if what I write is too small or not legible, let me know, because I can't really see what you're seeing. I can see it on my screen. Okay, so I told Balash yesterday that I would talk about alpha beta sets, but I've slightly reconsidered and decided to talk about the applications and motivation as well a little bit more than I was meaning to, because it seems maybe more in the theme of what you've been talking about. So here's the background for the story. So we take two self-similar sets on the line. So we're working in R. And we take a self-similar set X. So it's going to be the union over I in some index set of phi I of X, where phi I of little x is alpha I of X plus some translation S of I. And another one, which we'll call Y, which again is the union over J in capital J of psi J of X, of Y. And psi J of little y is beta J of Y plus some translation T of J. So that's the setting. And let's assume throughout the talk that dimension of X is no greater than the dimension of Y. The statements I'm going to make are asymmetric. So this is the right assumption to make unless you want to start dealing with different cases. Then the question that I'm interested in is, when does X affinely embed in Y? Meaning, when do there exist constants A and B with A not zero, and AX plus B is contained in Y? And I'll denote this relation by X embeds in Y. So I'm not going to say affinely all the time, because that's always going to be the case. So that's the question. So now you can see why I wanted to assume that the dimension of X is smaller than the dimension of Y. If the dimension of X were greater, clearly there's no such embedding. Affine maps preserve dimension. But if the dimension is smaller than the dimension of Y, and maybe we should also assume, just so it's, I think it's not actually necessary, let's assume that the dimension of Y is less than 1. So, so Y is a Cantor set. And so Cantor sets embedding Cantor sets, that's in principle, there's no topological obstruction. So the question is, when does the structure of the sets prevent this? And the conjecture, well, okay, maybe two facts before I state the conjecture. So the first fact is that you can reduce, and I haven't told you exactly what I want to reduce, but let's just make this an assumption. You can reduce to the case that X is a homogeneous fractal, so that all the contraction ratios are the same. Alpha I is equal to alpha for all I. So somehow, in all the questions I'll be talking about, it's easy to assume that all the contraction ratios in X are the same, but not to assume the beta J is constant. So that is not a reduction you can make in any of these problems, at least not a priori. And the second remark I want to make is that there's some connection between this question and intersection problems. So first of all, if you had a good bound on the intersection of X and Y, on the dimension of the intersection of X and Y, and it turned out that the dimension was less than the dimension of X, then of course, if you could bound the dimension of all the intersections of all the affine images of X with Y, and they were all smaller than the dimension of X, then you couldn't embed. Because you can embed x and y, then the intersection is x, and the dimension is not smaller than x. Actually, it goes the other way as well. So saying that x does not embed in y is the same as saying that when you look at all the affine images of x and you intersect them with y and you look at the dimension, then it will be less than, strictly less than the dimension of x. And actually, it's not, it's equivalent to a stronger statement, which is that the supremum over a and b of all these intersections is less than the dimension of x. So saying that you can't embed is the same as saying that if you take any affine image of x and intersect with y, there will be a definite dimension drop compared to the dimension of x. And the reason that these two things are equivalent is somehow that if you could find intersections of dimension arbitrarily close to the dimension of x, then by renormalizing and taking limits, you could somehow find an embedding. And probably all of you can imagine how that works. And if not, it's not going to be important for this talk. So I think that the second observation is, I believe, due to the Dejun, but I'm not 100% sure. I think it appears in his paper. So the okay, so what's the conjecture? So this is also due to Feng. And the conjecture under the reduction that I stated in 1 is that if alpha is not in the Q span of the logs, if log alpha is not in the Q span of the logs of the beta j's, then x does not embed into y. So this is an algebraic type abstraction similar to what,
Like you said that it is not an element and your own element, which is
yes, not an element, thank you. If log alpha is not commensurable to the beta j's in this sense, then you cannot embed x into y. So that's the conjecture. Okay, and so what's known? So Feng and Xiong proved that this is true when the dimension of y is small enough. I think, well, I believe that 1/4 was the bound, at least in, I maybe actually, when there are two maps, the bound is certainly 1/4, and when there are more maps, I think the bound is smaller. Let's just say this is in the case of two maps, but they have a result for any number of maps. And Amir Algom proved that it's true when the dimension of y is close enough to the dimension of x, or vice versa. So if you fix the dimension of y and you assume that the dimension of x is close enough to y, then you cannot embed x into y under the assumptions in the conjecture. And then there's, of course, one more case, which is based on the intersection theorem by Pablo and Meng. Of course, it's different papers, as everybody knows. But they can deal only with the case that y is also generated by the same contraction ratio. All maps have the same contraction ratio. So it's true when the beta j's are constant, and also the alpha j's are constant, as the alpha i's are constant, as I already said. In the non-uniformly contracting case, their method, at least out of the box, doesn't work. And so, the open case is what happens when the beta j's are not all the same. Okay, so that's more or less the situation. And the theorem that I want to tell you about is a joint work with Algom, myself, and Meng from I guess it'll probably be published this year, maybe next year. And we don't solve the conjecture, but we can prove a number of things. So one of the things is that if alpha and the beta j's are algebraic, then it's true. Right, so this is maybe a little bit reminiscent of what happens with the overlaps conjecture. And the mechanism is different, but it again boils down to the fact that for algebraic parameters, we have some kind of exponential separation. So I'll try to explain how that comes in, but it comes in a different way. And then we can also prove a few other statements. So actually, we can show that if if the alphas are algebraic, and if you look at the Q rank, the rank as a Q vector field of the span of the log alpha i's, and if the Q rank is less than the number of maps that generate y, then it's true. So, for example, if you take the middle third Cantor set, then you try to embed it into something which is generated by 3 contractions, and if you have enough algebraic independence, then you can't do it. That's one statement. And then we have sort of statements, maybe I won't state them exactly, but for typical alpha i's and beta j's, we can prove all sorts of things. If you fix, for instance, the beta j's, then there's a 0-dimensional set of exceptions for alpha i's. If you fix the alpha i's, there's a small dimensional, not 0, but small dimensional set of beta j's. Well, potentially potentially empty, but we can only prove small dimensional set of beta j's for which the conjecture is true. And such statements. I won't go into details about that. Okay, so that's the statement. And what I want to do in this talk is I want to outline what the approach is, and I want to explain how it raises questions about alpha beta sets, and I'll explain what an alpha beta set is. And the subject of alpha beta sets is maybe older than this question, and recently we sort of have a pretty satisfying answer to what you can expect for such sets, at least in general. And I'll try to explain how those things are connected. So are there any questions so far? Okay. So what's the approach? So as I said, let's assume that all the alphas are constant. So the set X is generated by maps that all contract by alpha. And let's write sort of script E of X and Y for the set of all the maps tau in the affine group of R that map X into Y. And so the affine map is a 2-dimensional group, right? And it's parameterized right by the contraction and the translation. And I will later, but you can already think of this. You can think of this set as a subset of R2. Just taking the contraction ratio as the first coordinate, let's say, so if tau X is AX plus B, I'll map it to A comma B. So since I'm looking at, maybe I should say I'm only looking at non-singular affine maps, A is never 0, so it's not onto the plane, but it's it's everything in the plane besides the x-axis. And so that's how I want to parameterize this. It's not a good parameterization of the affine group, but it is a parameterization that's as good as any other from our purposes. So what's the approach? So the approach is to show first that if there exist any embeddings then there are many embeddings. Maybe I'll say it differently. If E is not empty, then E is large. And then second, you want to show that if E is large, this implies that Y is large, too large. So for example, you could imagine maybe it's true that if you have a one-dimensional set of embeddings, then Y is one-dimensional, which would be a contradiction. And that's actually true. And I'll explain a little bit later why it's true, although that doesn't get you to the end of the conjecture, but that is a fact. So this strategy goes back at least to Fei and Sheng's paper, and I think many ideas go back earlier than that. So let me explain how this works. There really are two things that you can do, and they're both very simple. So here is X, and here is Y. Okay, these are Cantor sets, and they're Cantor sets in the line, but I'm going to draw them as sort of Venn diagrams because it's a little bit clearer. So suppose that you have a map, an affine map tau, that takes X into Y. So here we are, that's X, and here you have tau of X inside of Y. So there are two things that you can do. Maybe I'll draw tau of X a little bit bigger. So here's tau of X. There's two things you can do. One thing you can do is you can say, well, X is a self-similar set. So X has cylinder sets. I can look at a cylinder set. Maybe this is phi I1 up to phi IN of X. And since tau pushes all of X into Y, it also pushes the cylinder set into Y. So here I have tau of phi I1 up to phi IN of X. And so if you think of what this did, of what we actually showed here, we showed that if tau is an embedding, then for every choice of the indices I1 up to IN in capital I, also tau of phi, I'll just write it, tau of phi I vector I. So everybody knows this notation, right? I'm assuming that this is a conference on a very specialized subject. I don't have to define all the standard notation, but if I'm wrong about that, please. I can't see who's in the room. So should I define this?
I think we're all happy with that.
All happy, good. So right, so if tau is an embedding, then I've shown that I can pre-compose it with any composition of the maps that generate X, and I stay inside of the space of embeddings. So that's one operation. Then the second operation, I'll draw this again. Right, so here is X and Y, and inside of Y I have my tau of X. But then Y also is made up of cylinder sets, right? So this is the map, and Y is made up of cylinder sets, so it decomposes into cylinders, and there is going to, and I can find cylinders of Y that contain the image of X. So maybe, for example, it happens that this cylinder set is psi J1 up to psi Jn M of Y. And if that's the case, then I can further apply the inverse of this map, psi J1 up to psi Jm inverse, which maps the cylinder set back onto Y. And that, of course, maps the image tau of X.
The very right part.
Sorry?
I can try to.
No,
If you could just avoid like the last margin on the right, slightly obscure for us. So where the
I shouldn't write on the very right.
yeah.
Okay? Is that better?
Perfect.
Okay. I think you said it's okay.
Yes, show the face, maybe sometimes there will be gestures. Oh, yeah, sorry.
Yeah. Your country's not what you do.
I can't hear you very well when you're all talking together. I can't hear you very well at all, actually.
I did it, everything fine.
Okay. So my Zoom screen just popped up a message. Can you still hear me?
Yes. Yeah.
Okay. So all right. So where were we? So I was saying that we have this we have the cylinder set of y, and it can be mapped back onto all of y just by applying the inverse of the maps that generate the cylinder, and that maps the image of x to somewhere, right? And this is another image of x, and this image now is psi j vector inverse of tau. So what we've seen is that if you have a map tau in the space of embeddings, then you can find J1 up to Jm in the index set of the fractal y, so that psi j inverse tau is again in E of xy. And I want to emphasize that, so how much freedom do we have in choosing the j's? The j's were sort of forced on us, right? The j's depended on which cylinder set of y contained the image of x. So we don't have an infinite number of choices. Maybe we only have one choice, the empty string. Maybe we have one choice, but we can take the longest string or the smallest cylinder set of y that contains x. That's as much freedom as we have, but we can ensure that when we choose them, if we take the longest possible sequence, we can ensure that the cylinder set is more or less the same size as the image of x. So we can ensure that the Lipschitz norm of psi j inverse tau is more or less of order 1. Right? It's a standard. That's the standard thing. So we have these two operations that we can do on embeddings. We can either precompose, right? We can precompose, as we did over here, with a map from the compositions of the maps that generate x, or we can postcompose with inverses of the maps that generate y. And we can combine these two operations. So now this is sort of the standard thing that you do is you fix an infinite sequence of indices I, and you look at longer and longer prefixes of them. So you look at phi I1 up to In, and you compose that with your tau. And then once you've done this, you get a matching composition of the psi's. And all of these things are inside of the set of embeddings. And so I'll emphasize again that the j's depend on I1 up to In, but it's not very hard to see that it's going to be a linearly growing, the length of the j's will grow linearly. And as I said, we can arrange it so that the contraction ratio of this composition of three affine maps is of order 1. Okay, so now what is the contraction ratio of this thing? The contraction ratio of this guy, and maybe it's better to well, okay, we can just write it down. So it's going to be beta of J1 times up to beta of Jm, all with inverses. These are the contraction ratios of the psi's. Then we have the contraction ratio of tau. Then we have the contraction ratios alpha I1 up to alpha in. And if we take logs, then the log of the contraction ratio of this guy. And okay, so actually I'll take logs, but I want to divide the log. I want to take log in base alpha, so I'll divide it by log alpha. So then this product turns into a sum. Yeah, and I've sort of forgotten. Yeah, I told you that the alphas are constant, but I wrote it as if they weren't. But actually all the alphas are the same. So this is just, what this is just alpha to the n. I took the n prefix of the sequence I, and they all contract by alpha, so it's just alpha to the n. So when you take logs, you're going to get, well, the log of tau divided by the log of alpha. That's just a constant. And then I'm going to get n, which comes from this term, right? It's just log alpha of, log alpha over log alpha is 1, and the n from the exponent comes down. And then I have the betas with a negative sign, sum over from 1 j from 1 to m of log of beta j over log of alpha. And again, I want to emphasize that the way that I've chosen the beta j's, these all remain in a compact interval. I've arranged it so that the contraction ratio of this composition is always of order 1. So, all right, so what's the conclusion from this? The conclusion is that, again, let's look at, so if the space of embeddings, E of xy, is not empty, if I have one tau in there, then what I conclude from here is that when I take the projection onto the x-axis, or maybe I'll say not the x-axis, let me call this the projection onto the contraction coordinate. Every affine map has a contraction coordinate and a translation coordinate. I project onto the contraction coordinate. If I project the space of embeddings to the contraction coordinate, then it contains this set, a set of the form, whatever is written here, as n ranges over all the integers. I take longer and longer prefixes of this fixed sequence I. For each n, I rescale, I compose tau on the right with whatever the prefix determines. That determines what I compose with on the left. I get this contraction ratio for the composition, well, up to logs. Well, okay, I guess I have to exponentiate again if I want this to be precisely true. But up to the difference between taking logs and not taking logs, what I get is exactly that, is exactly the set of these numbers. And then the question is, how large can this set be? And that brings me to the definition of an alpha beta set. So this is, as I said, this is the second subject I want to talk about. So I'll define this generally. So let lambda be a set of real numbers. A subset E of the torus is a lambda set. Now, sometimes it's called a lambda multi-rotation. If the set E has the following property, that for every point in E, you can find a lambda in the set lambda so that x plus lambda belongs to E. And when lambda is just two numbers, alpha and beta, then a lambda set is called an alpha beta set. So that's where the term comes from. But I'm going to allow more than two numbers in lambda. And one more definition. So a lambda orbit is a sequence of points in the torus, in the one torus, such that the differences between xn plus 1 and xn are all taken from the set lambda mod 1. So a lambda orbit is a lambda set by definition, because every point in the sequence, if you take the next point in the sequence, that's also a point in the sequence, and it's obtained from the previous point by adding an element of lambda. And conversely, every lambda set contains a lambda orbit, because you just start from one point, and the definition tells you how to build a sequence from that point, at least one sequence. Maybe there's more than one choice. It shows you how to build at least one sequence starting from a given point in E, where each step you go to another point in E by adding an element of lambda. Right? So I guess maybe let me just draw a picture in case you've never seen this before. So you start from some x, and then lambda orbit says, suppose that lambda, has two elements, one green, one red. So you start from some x, and then a lambda or an alpha beta orbit is going to, just means, you take a green step, maybe you take another green step, you take a red step, you take a green step, take 2 red steps, 3 red steps, or 4. You keep going, you wrap around mod 1, and so on. Right, and the connection with what I discussed up until now is that this set, if I look at maybe I'll let me write this down explicitly. So, right, what we were saying before is essentially that if E of xy is not empty, then E of xy contains a lambda set, where lambda is the collection of the log beta j's over log alpha. Because why is that? Well, this formula over here tells you that when you start from, whoops, what happened? When you start from this point, then you iterate this renormalization procedure, then you're basically subtracting an increasing sequence of beta j's, except that occasionally you also add an n to bring you back to a compact interval. And that's essentially the same as reducing mod 1. Right? You just add the sequence of numbers. When you get negative enough or positive enough, you add an n to bring you back to a compact region. That's reducing mod 1, or maybe reducing to a slightly larger torus, but it doesn't, I don't want to talk about, that's just a technical point. So if we want to say that the set of embeddings is large, then the information that we have is that it contains a set of this type. It contains a lambda set. And we know from the assumptions of Fink's conjecture that this set is independent over the rationals. That was the conjecture, that if this set is independent, then there are no embeddings. So we're assuming that this is independent, and we're now hoping to show that a lambda set is large. Because if a lambda set for a Q-independent set of gaps is large, that means that the space of embeddings is large, and then we have some hope of proving the conjecture. So okay, so let me go. So going back just to the general question. So alpha beta sets were first considered by a guy called Engelking, I think in the 1950s or 60s. And I've never read the paper because it's in German, and it's I don't know German. I could probably ask ChatGPT to translate it for me, but I haven't. But he was interested in the topology of such sets, and I think from what I've read in other places, he believed that maybe they should always have non-empty interior. Maybe I should say that the simplest case, maybe this is the first remark I should make, is that if lambda has just one element in it and lambda is irrational, then a lambda set is simply has the form x plus lambda n for n in the integers, and this is of course dense in the torus. It's just an irrational orbit. So I think initially people thought that, okay, if you have two irrational numbers and they're not related, it doesn't matter which one, in what order you add them together, you should still get a somewhere dense set. And actually, one thing you can see right away is that suppose you have two irrational numbers and you start adding them in some order you don't have any control over it, if you add if there are arbitrarily large intervals in which you only use one of the numbers, then you're getting arbitrarily large pieces of an irrational rotation, and you're again going to be dense. So in order for a lambda set not to be the whole torus, you definitely have to use both or multiple rotations or gaps, and you have to use them frequently. You can't forget about them for too long. So you have to alternate with some positive frequency. So I think maybe that was the original reason people thought that you should always have an empty interior, but Katz-Nelson proved that that's not the case. This is Katz-Nelson, I think from 1979, if I'm not mistaken. I'm quite unsure of the date though, but I think that's the case. And he proved two things. First, he proved that if you take any subset, let's call it maybe Z of the torus, countable, then there exists an alpha beta set, E, whose closure is disjoint from Z. And so that tells you in particular that you can have nowhere dense alpha beta sets. And they can be nowhere dense in any way that you want. You can choose any countable set and avoid it, right? So that's one thing. And the second thing that he proved is that there exists an alpha beta set, E, so that the Hausdorff dimension of E is 0. Maybe I should say one more thing. I do have to quantify this. So actually, it's trivial that there are alpha beta sets with dimension 0 because you can take a finite alpha beta set. And so, of course, the point here is that there exists an infinite alpha beta set. And also here, we want an infinite alpha beta set. The way that you can get a finite alpha beta set is precisely when you have a rational dependence between the gaps and the number 1. So it's a slightly different statement than what we made before, but there's a simple arithmetic condition that characterizes when there can exist a finite alpha beta set. And so we're not considering that case, we're considering the case of infinite alpha beta sets. And then it's not trivial at all that there exist 0-dimensional ones. Okay. Most talks that I give, I can say safely that there's no difference between Hausdorff dimension and box dimension, but here that's not the case. So about a decade ago, I think actually in 2016, Huang and Sheng proved that if E is an infinite alpha beta set, then the box dimension of E is at least 1/2. And in general, if E is the lambda set, then the box dimension of E is at least as big as 1 over 1 plus the Q rank of E. I believe this is the right formula. So actually for two elements, it's a little bit better than you would expect. And there's a little bit of gain in the denominator. But you do get, in all these cases, you do get a positive box dimension. Even though the Hausdorff dimension can be 0, you always get a positive box dimension. And this was improved by a number of people in several ways. So there's Han Yu proved that when lambda is contained in is a set of algebraic numbers, then you can improve the lower bound to 1 over the Q rank. Sorry, I said the Q rank of E, but I meant of lambda. Sorry. It's, Q rank of E is infinite usually, but the Q rank of lambda. So you're interested in the Q rank of the set of possible gaps, not of the lambda set itself. So that's an improvement. And then Simon Baker, I think a little bit later, proved that if you have a Liouvillean alpha and a beta which is not Liouvillean, then the box dimension of E, so E is an alpha beta set, actually has to be 1. And both of these results sort of point to the fact that you can improve this in some cases. I think there are also results for like generic alpha and beta. I don't remember who by. I apologize if they're sitting in the room. The point is, I think it was believed or hoped that maybe it's always the case that the dimension is 1. Okay, but that's not true. So that's another theorem that I proved a little while ago, that there exist alpha and beta and an infinite alpha beta set E, so that the box dimension of E is 1. Actually, I should maybe say that I think what Simon showed was that the upper box dimension of E is 1. Sorry, and what I said here is wrong. I should have said 1. So, right. So, in other words, the Feng-Shung bound is sharp. If you have, well, actually, I don't know that it's sharp in all cases. I know that it's sharp for when you have two, when you have alpha and beta, when lambda consists of 2 elements, it's sharp. And I believe that it's sharp also in the general case, either that or use bound. I don't know which, and I haven't tried to work it out, but definitely, one of them is sharp. Whichever is the right one is sharp. Right. So that's sort of the story of alpha beta sets. And I'm not going to say very much. I think I'm not going to say anything about the proof of this theorem. What I would like to do is go back to the sketch of how it's used to understand embeddings and explain some of the new ideas there. They raise new questions about alpha beta sets, and then I hope to be able to explain how sort of exponential separation comes in, exponential separation for the lambdas. So, okay, so what I explained before, right? We had our set X, we had our set Y, and if we had an embedding tau of X into Y, then from tau we we could get a new we could get many new maps they had the form psi, let's say j vector inverse tau phi I vector. So we had freedom to choose I any way we wanted. And then once we chose I, we got j sort of determined by for us, provided that we specify that we want the contraction to be of order 1. Okay. So now I want to think about, I don't want to think about individual embeddings. And this is sort of the new idea, which is to think of the space EXY as the space that we're working in. And to think of this operation that takes tau to a new version of tau as a renormalization operation on the space of embeddings. So like I told you before, the space of embeddings I'm going to think of as a subset of R2. I'm going to have the x-axis will be the contraction ratio, and the y-axis will be the translation. And then E is some kind of blob. I mean, it's not an open set or anything like that. It's some kind of fractal set or something, some kind of set. It's closed. I mean, the one thing you can say about it is that it's closed. It's a closed subset of R2. And what I told you so far is that when you project down from this subset of R2 to the space of contractions, then down here, up to a log, you have a lambda set, and therefore the box dimension is positive. Not very positive, but maybe a tiny bit positive. And if the projection, okay, log is a smooth map, and you projected a projection is a Lipschitz map. So if the box dimension downstairs is positive, then we know also that the box dimension of EXY itself is positive. So I know that this subset is not too small. May have Hausdorff dimension 0 for all I know, but its box dimension at least is somewhat positive. All right, now how do we boost box dimension up? So there's a general scheme. If you have something that has positive box dimension, then you know that you can find little parts of it that up to a smaller resolution look like they have positive Hausdorff dimension. Right? That's basically the idea of Aswad dimension. So if I take a little dyadic cube that intersects my set E, what I would like to do is I'd like to take that cube and magnify it back up to macroscopic scale, and somehow take limits. And when you do that in Euclidean space, you can go from positive box dimension to positive Hausdorff dimension. Right? That's a sort of standard thing. The problem is that when you take a dyadic cube inside of E, or that intersects E, and you magnify it in a Euclidean way, you don't stay inside of E. There's absolutely no reason that a Euclidean magnification of the space of embeddings should give you embeddings that take X into Y. There's absolutely no connection between the Euclidean structure and the sort of the structure of the space of embeddings. But what you can do is, instead of magnifying it using Euclidean, just using a homothety, instead of that, you can use this operation. Right? Why? Well, you take your little cube, and you also, so that you chose the cube, you chose I1 up to IN. And then for every tau in this cube, you get this psi j inverse tau phi I. And the two things to note here are that, first of all, the j's don't really depend very much on which tau you chose. Because if the taus are constrained to a small cube, then they differ by a very small amount. And if the i's are not too small relative to the size of the cube, you're going to end up with images of X that are very close together. And so when you ask which cylinder of Y are they sitting inside, they're sitting inside the same cylinder. And so the psi part of this map will be the same. So that's one thing. And the important thing is that this operation keeps us inside of the space of embeddings. Okay, but what does that give us? Well, you can calculate what this, you can explicitly calculate what this operation does. If tau of x is ax plus b, then what is this thing as a function of x? Well, it's going to be some a prime x plus b prime. A prime, that's very easy. A prime is going to be just the Lipschitz norm, or the contraction ratio of psi j inverse, times the original contraction ratio, times the contraction ratio of phi I. And what's b prime going to be? Well, that's a little bit uglier, but basically it looks like this. It's going to be psi j inverse, Lipschitz norm of that, times times not b, but times phi I of 0. This is the translation constant of this map, plus a constant, which is independent of well, constant may depend on j, I think, but a constant which essentially independent of I. Now, why is this important? Well, so first you have to think what exactly when tau varies inside a small cube. Suppose that the cube has side 2 to the minus n. It's a small dyadic cube. Its contraction ratio varies by that much, and its translation constant varies by that much. Now, this formula over here, the new contraction ratio that we get, is going to vary by the same amount because you see we've chosen things, we've chosen things so that these two contractions, the contraction of the psi's and the contraction of the phi's, cancel out. So the new contraction ratio varies by 2 to the minus n. I mean, as a prime varies by some amount, this product varies by more or less the same amount. So I haven't actually expanded the contraction ratio at all. This operation has been pretty much neutral up to a multiplicative constant bounded away from 0 and infinity. It's been neutral on the contraction ratio, but it's not been neutral on the translation part, because here psi j inverse is more or less 2 to the n. It rescales by approximately 2 to the n. And on the other hand, the way that phi comes into it is as a constant, as this constant. So, in other words, here's what we get. If I start with e of xy and a little dyadic cube inside of it, and I perform this renormalization operation, then it takes the little cube back into e of xy. What does it do, though? It doesn't change the width very much, because the width is the contraction ratio. So I'm going to get, but it does rescale the translation part by 2 to the n. So I'm going to get something that looks maybe like this. It's going to be tall and thin. Its height will be sort of macroscopic. The width is still going to be 2 to the minus n, like it was before. And more than that, what am I going to see here? Well, as I vary the vector I, it's what I'm getting if I look at the translation part that I'm getting in the vertical direction. What I'm getting is a linear image, well, I've slightly mangled this, but yeah, I think there's an A in here which I didn't write down before. So I'm getting a linear image of A by a map as parameterized by phi I of 0, by the translation part of the phi's. Why is that important? Well, it's important because I'm in a position to apply a projection theorem. Because the phi I of 0 is essentially a point in the attractor X. And X has positive dimension. So if I choose, the choice of I is essentially choosing a projection from a positive dimensional set. And what I get in the vertical part of the image of the small diagonal cube is essentially a projection. It's like a quote unquote random projection of the cube, but rescaled. Okay, so I'm starting to run out of time. In fact, I'm almost out of time, so just let me get to the main point. The main point is you can apply Orponen's projection theorem and conclude that for a random choice of phi I, which essentially means choosing a point in X, according to the self-similar measure, this vertical strip that I drew, well, you have to go to some kind of limit, but it has Aswad dimension equal to the box dimension, or the Aswad dimension, of the space of all embeddings. And so what you conclude is that you have this strange situation. You have this E of xy, which has positive box dimension, but all of that dimension is actually realized inside of the set, sitting on vertical strips. And you can do another approximation and actually show that you have that much Hausdorff dimension even on these strips. So you have a set whose vertical slices, in some sense, typically, but typical here is not well defined, you have a set whose vertical slices have the same dimension as the set itself. And that should imply that the projection of the set in the transverse direction should have dimension 0. However, the projection is a lambda set. It shouldn't have dimension 0, except that everything I've said is, of course, very imprecise and not correct. And what you actually get, is that if you look at the set of vertical lines in E of xy, such that the dimension of the line is equal to the dimension of EXY itself, if you look at this collection of vertical lines, then they sit above a lambda set. So if you look at the x coordinates of these vertical lines, they form precisely an alpha set. And the alpha set we know has positive box dimension, maybe very small. It has some positive box dimension. And you think you should get a contradiction from this because you have a set E whose dimension is realized on these vertical lines, and the set downstairs has positive box dimension. However, you don't have enough uniformity of the dimension of the vertical lines to sort of use a Fubini argument here. The problem is that these vertical lines, they might have positive dimension concentrated on the tiny little ball. You could, the way that the dimension is positive on each of them can be very different. And you need to do a step that uniformizes it. And you can do it. You can make sure that most of these strips look sort of the same, right? But what you conclude from that is that the vertical strips that sort of all look the same don't sit above a lambda set. They sit above a subsequence of a lambda set, which has positive density in the lambda set. And so you would like to say that we know that a lambda set has positive box dimension. You'd like to say that when you take a positive density subsequence of a lambda set, you still have positive box dimension, and that would finish the proof, but it's not true. So it's another thing that I was hoping to say more about, but there are examples of alpha beta sets where when you pass to a positive density subset of them, the box dimension suddenly drops to 0. However, when can you ensure that passing to a 0 density subsequence doesn't drop the dimension to 0? You can do that when you have some kind of exponential separation of the gaps. So when the gaps, I really am out of time at this point, so I won't even state it, but there's a sort of natural Diophantine condition on the gaps, which when it is satisfied, not only guarantees positive box dimension for the lambda set, it guarantees it for any subsequence. When you know, and then inside of this EXY, what you know is that the dimension of EXY is realized on the fibers, and that they sit over a positive dimensional set, and the fibers all sort of look the same, and that's your contradiction. So I'll stop here. I'm sorry, I went over time.
Your questions for Mike? Maybe I can make a slide. I somewhat missed, how do you conclude that in all of those lines they are all full dimensional?
How do you conclude that they're all full dimensional? Was that the question? So it's a combination of, you don't get it for all the vertical slices, right? You start with E of xy. You know that it has some box dimension, right? Some box dimension delta. Okay, so then what you can do is you can find smaller and smaller boxes inside of E. When you magnify those squares in a Euclidean way, they converge to something delta dimensional. That's sort of a CP chain argument or an Aswad dimension argument. That's kind of a standard thing. Okay, then you say, well, let's do this non-Euclidean magnification. We magnify each of these guys, and actually not just each of them. Inside each of them, we take a decreasing sequence of dyadic cubes of an increasing length. That's sort of it helps regularize things if you do that. And we magnify each of them. So each of them will give us a sequence of strips. Each of these strips looks like a projection of the Euclidean cube. And after the projection, it's magnified. Now, these Euclidean cubes, when we project them by Orpinen's theorem, if we choose how we project them in a sort of random way, even with a very small amount of randomness, we get full Aswad dimension. So on these cubes, I'm sort of seeing all the delta dimension of E. When I magnify them with this renormalization operation, I'm seeing a good projection of them on the vertical direction, and they're staying very narrow underneath. And this sequence of strips that I get from each of the cubes looks like a piece of a lambda orbit. And then you have to take a limit in some way, sort of a Hausdorff limit or something like that. And you have to do some analysis to show that the properties that you want pass to the limit, but they do. So that's essentially what we do. And then after we do that, we get like I said, we get some lambda orbit on the x-axis, and above each of them we have what looks like a fairly regular, like a random measure from a CP chain, from a one-dimensional CP chain of dimension delta. And the reason, but they're not you don't have enough uniformity. To get uniformity, you have to do kind of an Egorov argument. The sequence of vertical strips is sort of looks like a stationary process. You can make it look uniform by passing to a subset of 99% of the measure of the underlying space of the process, and then you throw out like 1% of the vertical strips, and that's unfortunately can cause the dimension of the base to drop to 0, as I tried to explain. That's the argument.
Thanks. Any other questions, comments?
Sorry, will I use the entropy to study the box dimension?
We use sort of the CP chain technology, which entropy is part of it. We don't use entropy in a direct way, but we do use the fact that when you have a positive Aswad dimension set, then you can find a sequence of boxes so that on those boxes, when you run a CP chain for some increasingly long amount of time, you approach a delta dimensional CP chain in the space of distributions, and then we work from there. I don't think we use entropy explicitly here in any place, but it is underneath.
No other questions. Let's take Mike again.